Hi, in this video, we want to take a look at discrete probability distributions. Now, we're going to go over the PowerPoint slides from Essential Biostatistics by Bernard Rosner, which is a Cengage textbook. All right, so with the discrete probability distributions, the ones that we're going to go over, we're interested in the situation where I have numbers and I have a gap between those numbers as my random variables. So this is going to be something like 0, 1, 2, 3, 4, 5. You'll notice that I can't get 1.5 if I have a counting number. So with the discrete probability distributions, that we're saying that we have non-continuous random variables. Now, from this lecture, the most important thing to walk away with, is name of the probability distribution and when you use it. Or if you can remember those two things in real life when you're working, you go, hey, I'm in a situation where I need I need a distribution that has these features. I remember, oh, it's the Poisson distribution. I go look up the information about the distribution and I go do my modeling as I need to. So absolute most important thing to learn when it comes to probability distributions is the name and when you use it. Because what'll happen in real life, you'll have a problem. You'll go, hey, I recognize that I'm in that situation for my statistics class. I remember the name of the distribution. Now I'm going to go and look up the information related to it. All right, so we're going to talk about discrete random variables. We're going to talk about probability mass functions. So here, what we're going to do, we're going to say that there's a math equation that gives us the probability that a particular value will be observed when we're looking at the random variable. We're going to look at the cumulative distribution function. We're going to look at the expected values, so the population average, and we're going to look at the population variance. We'll look at permutations and combinations, and then we'll look at the binomial distribution and the Poisson distribution. All right, the binomial distribution, we're in the situation where I have a finite number of events, and I want to know how many of those events are success or failure. So for each of those events, I have two possible outcomes. So, it could be like, we know that we have 10 people. What is the probability that 2 of them are female? What's the probability that 8 or more are female? One thing that's critical about this is that the number of events, the number of cases is established beforehand. It's not a random event. So we know the number of times something happens, and we want to know the number of successes. The number of successes is the random variable. Poisson distribution, all right, for this is in biostatistics, this is one of the most important distributions because we use this for counting. So I'm in the situation where I have 0 or 1 or 2 or 3 or 4, so on. We will use this distribution when I'm interested in the case where first we start at 0, then we get to 1, then we get to 2, then we get to 3, then we get to 4, and so on. So this would be something like number of collisions at an intersection during a month. Well, we start out at the beginning of the month with 0 collisions. Then somebody hits somebody else, that's 1. Another person hits somebody else, that's 2. Another person hits somebody, that's 3. We had to go to 1, then 2 before we could get to 3. That's different than the binomial distribution. With the binomial distribution, we could have, let's say, I've got 10 employees. I want to know the likelihood of 3 females. Well, it might, if I walk on the job as the manager, get hired to manage the team, to me, I just have instantaneously 3 at one time. Like, there is not a sequential aspect to it. All right, so random variables. A random variable is a function that assigns numeric values to different events in a sample space. 2 types of random variables are discrete and continuous. A random variable for which there exists a discrete set of numeric values is a discrete random variable. A random variable whose possible values cannot be enumerated is a continuous random variable. Now, if you've taken advanced calculus, mathematical analysis, you'll know that there's a little bit more to the idea of a continuous random variable. in this series of videos, in this course. Don't worry about it. If we say continuous, think that any number between any other possible value is possible, that it's a continuous line of values. While discrete, I have gaps between my possible values. Those descriptions are not 100% correct if you take mathematical analysis, advanced calculus, but that's good enough for our purpose. All right, the probability mass function for a discrete random variable. The values taken by a discrete random variable and its associated probability can be expressed by a rule or relationship called a probability mass function. All right, so here, what we've got, we're going to have a function going from the possible value to the probability of observing that value. A probability mass function, sometimes called a probability distribution, you'll hear me say, I like to say distribution personally, is a mathematical relationship or a rule that assigns to any possible value r of a discrete random variable x the probability that x is equal to r. This assignment is made for all values of r that have a positive probability. All right, so what we're saying is that this probability here, the probability of seeing r as the actual value, there's a math equation for it, really. So that's all we've got, really. All right, so probability mass function can be displayed in a tabular form or can be expressed as a mathematical formula given the probabilities of all possible values. And so here we're looking at the probability mass function for a hypertension controlled example. Probability of 0 is less than 1%. Probability of 1 is just under 8%. Probability of 2 is a little bit more than 1 out of 4. Probability of 3 is a little bit more out of 4 out of 10. And then probability of 4 is just under 1/4. And so this defines a mathematical function between 1, 2, 3, 4, and the probabilities. And when I say function, I mean in the sense of like college algebra function. The probability of any particular value must be between 0 and 1. So remember, probabilities are always between 0 and 1, and they always add up to 1. Now, the relationship of probability distributions to frequency distributions. Frequency distributions is described as a list of each value in the data set and a corresponding count of how frequently we see the value in the data set. If we take each count and it's divided by the total number of points in the sample, then the frequency distribution can be considered as a sample analog of a probability distribution. It works out under most situations that if I go through this count and divide by the total number, then the value I observe will be pretty close to the mathematical formula. It won't be exact, but it will be close. Frequency distribution gives the actual proportion of points in a sample that corresponds to a specific value. Hence, the appropriateness of a model can be assessed by comparing the observed sample frequency distribution with a probability distribution, also called the goodness of fit. All right, so what we're talking about here in this paragraph is that I have some data, and I believe I can model that data using a particular probability distribution function, probability mass function. What I'm going to do, I'm going to look at the frequencies, and I'm going to look at the theoretical probabilities that you have for each value. I'm going to compare them. If they're close to each other, then that gives me confidence that I chose the correct theoretical probability mass function. And so here is an example of what we've got going on. So we're looking at the observed frequencies and the theoretical probabilities. All right, so here are the values that are observed. Here is the probability theoretically, and here are the actual values that we observed. So we see, less than 1% and 0. We see that, so here we have none. So Theoretically, less than 1%, and we see 0. Theoretically, 8%, we see 9%. Theoretically, 27%, and here we see 24. Theoretically, 40%, and I see 48%. Theoretically, 24%, and I see 19%. So these are pretty close. Now, the larger my data size, the closer I would expect these numbers to be to each other. So the probability mass function derived from the binomial distribution is compared to the frequency distribution to determine whether the drug behaves with the same efficacy as predicted. So if I see a big difference between these probabilities and these frequencies, then I have probably chosen the wrong probability mass function. All right, so now let's talk about the expected value of a discrete random variable. If a random variable has a large number of values with a positive probability, then the probability mass function is not a useful measure. Measure of location and spread can be developed from a random variable in much the same way as it can from samples. The analog of the arithmetic mean, so that's where I take, I add up all my observations and divide by the number of observations, that is the sample average. We're going to talk about the population average or the expected value. So the expected value or the population mean is the true theoretical average. Now, we will never truly know what this is, but we can get a good idea of it. The expected value of a discrete random variable is defined as taking the observed value times the probability that it will be observed, add it all up. And so here is the theoretical probabilities. The expected value, I multiply here, multiply here, multiply here, multiply, 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 and then multiply. After I do all the multiplications, I add all the products up. Now, the variance of a discrete random variable, the analog of the sample variance for a random variable is the population variance, also called the variance of a random variable. And we will frequently denote this as V of x, var of x, or sigma squared. All right, so how do we compute this? All right, what we're going to do is I'm going to take the observed value minus the expected value that we talked about on the last slide, square it, multiply the by the probabilities, then add it all up. Now, it works out that this is equivalent to taking the expected value of the square of our observations minus the expected value squared. And that's a straight calculation using just a little bit of calculus. Now, if I want the standard deviation of the population, what I'm going to do, I'm going to take the square root of the variance, which should feel very natural after we took, because we do the same thing to go from sample variance to sample standard deviation. So the expected value gives us an idea of central tendency of where is our probability distribution along the real line. The variance gives us an idea of the spread of the distribution. Approximately 95% of the probability mass function falls within 2 standard deviations of the mean of a random variable. Now, this is not always 100% true, but see the word approximately. Now, a cumulative distribution function, what this does is that this adds up the probabilities as I go from the lowest observed value to the highest. What I'm going to do, I'm going to take, if I go 0, 1, 2, 3, 4, 5, so on, I'm going to take the probability of 0. Then I'm going to take the probability of 0 plus 1. Then I'm going to take the probability of 0 plus 1 plus 2. Then I'm going to take the probability of 0 plus 1 plus 2 plus the probability of 3. Then I'm going to take the probability of 0, probability of 1, probability of 2, probability of 3, probability of 4, add them all up. I'm going to keep on doing that. Now, notice that I keep on adding more things together, and because probabilities are always positive or zero, we are increasing the probability, or we're increasing the sum as I go from left to right. So here, this is the probability of seeing, 1 or less. This is probability of seeing 2 or less. This is probability of seeing 3 or less. And we just keep on going like that. So for a discrete random variable, the cumulative distribution function looks like stair steps. And it'll look smoother if I have more possible values. For a continuous random variable, this is going to be a smooth curve. All right, now let's talk about permutations. All right, so permutations. What permutation tells me is that if I have 5 people and 2 of them are going to get a prize, one is going to get a new car, another one is going to get a gift certificate to a restaurant, and then everybody else gets nothing. Then the permutation of 5 choose 2, or permutation 5 2, will give me the number of ways that we can select someone to get a new car, then the person who gets a gift certificate, then everybody else loses. So in a matched pair design, each sample and case is matched with a normal control of the same sex and age. Once the first control is chosen, the second control can be chosen in n-1 ways. The third control can be chosen in n-2 ways, and so on. Thus, the first 2 controls can be chosen in n times n-1 ways. The number of permutations of taking this is npk. All right, so imagine a situation where we have 3 prizes and we have 100 people. First prize is that they get a new car. Second prize, they get a week's vacation in Hawaii. Third prize, they get a gift certificate to a restaurant. All right, now, something about this, as they're drawing names, and nobody wins more than once, by the way. In this situation, nobody wins more than once. In this situation, order matters. All right, it's much better to be the first person to win than it is to be the third person to win. The gift certificate versus a new car, I would definitely want to be the first person to win. This is different than the situation where everybody wins the same prize. If everyone wins the same prize, it doesn't matter if I'm the first person called or the last person called. But when we have new car, trip to Hawaii, or a gift card, order matters, because being, being the first one called or being the second or being the third is a very big difference for us. When order matters, we're going to use permutations. So this represents the number of ways of selecting k items of n where order is important, where order matters. And so here's how we do the calculation. And so here, if I do permutation of nn, then that's going to be all the numbers 1 to n multiplied together. And we'll call this n factorial. And so this will be n exclamation point. All right, so another way to write this using the factorial notation is that I'm going to take n factorial and I'm going to divide by n minus k factorial. And that will give us a way of computing this. Now, notice if you're doing it by hand, you're going to have a lot of things cancel in this fraction. A lot of things will cancel. Or here, the n minus k cancels with n minus k. N minus k minus 1 cancels with n minus k minus 1. So on down the list, all the way to 1. And only these items will be left. Now, combinations. All right, so permutations, we use those when order matters. Combinations are when order does not matter. So think about the situation where I have 10 people, everybody gets exactly the same prize. I'm going to pull names out of a hat. The number of ways to select people to win is a combination. It's going to be n choose k is how we word it. So in an unmatched study design, cases and control are selected in no particular order. Thus, the method of selecting n things taken k at a time without respect to order is referred to as the number of combinations. And so this is how we write this. So it's going to be numbers n down to n minus k plus 1 multiplied out divided by k factorial, or we can write it as n factorial will divide by k factorial n minus k factorial. Now, it works out that as long as I have numbers that make sense for doing these calculations, that n choose k is equal to n choose n minus k. And here just shows that this is correct. All right, now let's talk about the binomial distribution. The binomial distribution is I have a pre-established known number of events, and in each of those events, I have success or failure. Think about flipping a coin. If I know if I'm going to flip a coin 10 times, and that 10 is a hard fixed number, and I go through and count the number of heads, heads is a success, tails is a failure, then I'm using the binomial distribution. Now, when I use the binomial distribution, I'm assuming that my observations are independent and identically distributed to each other. So I have the same probability of success every single time. Imagine a situation where it's a trick coin. It's either both heads or both tails. Then in that situation, when I'm flipping a coin, once I get heads or I get tails, I know the rest of those flips. So if I'm flipping 10 times, I have that trick coin. Once I see heads on the first one, the rest are also going to be heads. If I flip and I see tails as a trick coin, I know that all of them are going to be tails. That is not the binomial distribution, because in the binomial distribution, we have to have independent, identically distributed. All right. So the probability of success is assumed to be constant for every single flip, and a previous event has no influence on the other events. And so here are some examples. And here is my equation for figuring out the probability of a particular number for the binomial distribution. Now, you'll notice here that if we call an x a success and O as a failure, then 5 choose 2 will give me the number of ways that I can distribute the x's among the o's distinctly. And here's my formula for the probability. The distribution of the number of successes in n statistically independent trials where the probability of success on each trial is zero is known as, this should be a P, is known as the binomial distribution, has a probability mass function given by this. Now, something that's important is that we know the number of events, the number of times I flip a coin. We don't know the number of successes. And so this is showing the relationship here that if I have the probability that x, so x is a binomial random variable with this many trials and success p probability, and y is a binomial random variable with same number of trials, but its probability of success is 1 minus p, then we can see that the probability that x is equal to k is equal to the probability that y is equal to n minus k. So we have like a symmetry going on here. All right, now, whenever you're going to work with this, realistically, you're going to use a computer to do the calculations. If you're going to be using Excel, you can use the binom dist function to do the computations for you. D binom, P binom, R binom, and Q binom will give you tools in R to tackle this. Now, it works out for larger values of n that factorial calculation can be a problem. Did you see like how many multiplications I've got going on? Well, it works out that if I'm using the binomial distribution with a large number of trials, computationally, the computer can't handle it. Now, the number exists, the number is there, but the computer itself can't handle those factorials. What we can do is we can make an approximation using the normal distribution. All right, so it works out that in a lot of situations, I can approximate what I'm interested in by doing a little bit of mathematics to convert what I'm interested in to matching approximately the normal distribution, figure out what I want, then convert back. Usually in general, if you just tell SPSS, Python, R, whatever to do the calculations, it will automatically do this for you. And so here is an example of just running the computations. So here is R and here is Excel. So do some calculations for us. All right, the expected value and variance of a binomial distribution. All right, the expected value of a binomial distribution is n times p. Number of trials times the probability of success. That's my expected number of successes. Now the variance is going to be n times p times q. That's the number of trials times the probability of success times the probability of failure. Now that variance will be largest when p is closer to 1/2. It will be largest when it's exactly 1/2, in fact. And so here is how we do our calculations to work this out. If I sit down and just do, a little bit of calculus, simplify the factorials and start working this out, it's pretty easy to show that this works out the way we want. And then here for the variance, I just take the value minus the expected value and just crunch this out. There's actually an easier trick than what's shown. This is correct, but this is not how you would compute this if you were doing like a mathematical statistics course, doing stat theory. All right, so here we can see this is the variance of one trial binomial random variable. We can see that the variance is largest at 1/2 and it's smallest at 0 and 1. The expected value is equal to n times p. And we can see that the variance is smallest, closer to 0 and 1. And so here are some bar plots just to let us know what does the binomial distribution really look like. And you'll notice that when I get to larger values of n, and I have probability of 1/2, this looks a lot like a symmetric bell curve. We can see that when I have smaller probabilities and larger probabilities, things are heavily weighted to one side. Now the Poisson distribution. This distribution is the one that I'm going to use when I'm counting things, where I go from 0 to 1 to 2 to 3. So think about like collisions at an intersection. We start out with 0 collisions, then there's 1 collision, then there's 2 collisions, then there's a third and a fourth. If I go through that process of counting and generating my random variable, then it's probably a Poisson distribution. Now, the Poisson distribution is used a lot in biostatistics. It's probably the most important discrete distribution there is, period, overall. Now, yeah, I disagree with this. I would say it is the first most frequently discrete distribution, but the author and I disagree. So here is the probability mass function. So we know, so it's going to be e to the power of the negative times the average to the power of k divided by k factorial. K goes from 0 to infinity. And if you've taken calculus, you should recognize that this mu to the power of k divided by k factorial, if I was to add up this part, ignoring that e, it would in fact add up to e to the power of mu. Now, there's going to be direct connection to time with a Poisson distribution. So think about my collision at an intersection example. Well, if I know the rate at which, on average, the average rate for which there's collisions at an intersection, can I extend that to knowing, so I know the rate over a week or a day or a month or whatever. Can I extend that rate to cover the whole year? Yes, I can. So let's say that I know on average that the rate of collisions at an intersection for one day. Well, if I want it for the entire year, I multiply that number by 365. So the point of this right here, this lambda times t, that t is the amount of time I'm interested in. So if I knew the rate for one day, and instead for my project, I need to know the rate for 1 week on average overall, I multiply by 7. The t is 7. So lambda is the expected number of events per unit time. Mu is the expected number of events over the entire time period. For the with the binomial distribution, the number of trials is finite, and the number of events can be no larger than n. The Poisson distribution has no upper bound. The numbers could be anything. Like potentially, we could have 1 million collisions in a month at an intersection. Potentially, it could happen. Unlikely, but it could happen. And so Poisson distribution, we're taking the point of view when we use this one that there is no upper bound to what I potentially could see. So here are some bar plots of the probability mass function for the Poisson distribution. You'll notice that the distribution tends to become more symmetric as the time interval increases or mu increases. Now, to compute the probabilities, once again, you want to use a computer. Potentially, you could use a graphing calculator. You could use pencil and paper. You could work it out with a scientific calculator. Just have a computer do it. So here is Excel, is the Poisson function. Now, the expected value and the variance for the Poisson distribution uses really the same formula. I take observed value times probability of observed value, multiply, add them all up. That's my expected value. And then for the variance, I take potential value minus expected value, square it, multiply by the probability of that particular value, add it all up. That gives me the variance. So if we have a data set from a discrete distribution where the mean and variance are about the same, then we can usually treat the random variable as being a Poisson distribution. So if I look at my data, I see my sample average and my sample variance are close to each other, then I'm going to be looking to use the Poisson distribution. Now, if that doesn't work out, frequently in biostatistics, if I see that the sample average is much less than the sample variance, then I'm going to be looking to the negative binomial distribution, which we're not going to cover here. But you can know it, and when it comes up, you can look it up. So if the variance is the sample variance is approximately equal to the sample average, then I believe the Poisson distribution would work out well. Now, also, I have to be working with count data. And so here, we can work out the values. And remember that if I need to change the time scale, I change my expected value to update my Poisson distribution easily. All right, so now if I'm in a situation where I want to use a binomial distribution with a large N and small p, then it's possible for me to approximate the Poisson distribution by setting mu equal to n times p, and this then just saying I'm going to accept the Poisson distribution probability as the binomial distribution probability, and things will be, close. Now it's an approximation. The reason why we need this is because of those factorials. All that multiplication, if I have a large n, it can work out that the computer can't do the calculation for us. All right, so anytime I have a large number of trials, large number of events in binomial distribution, and the probability of success is very small, I can be looking to the Poisson distribution to make my life easier so I can get the probabilities easier that way. All right, so summary. We talked about random variables and distinction between discrete and continuous random variables. We talked about specific attributes of random variables, including the notion of probability mass functions, probability distributions, cumulative distribution functions, and expected values and variances. We talked about sample frequency distributions from, in relation, I'm taking the sample frequency to the theoretical distribution to compare. And so we have the idea of a sample mean and sample variance are analog to the expected value or population mean and population variance. The binomial distribution is when we are interested in the situation where I have a known number of events and those events are classified as success or failure, two possible levels. That's why it's binomial. I could now success, failure, I could do male, female, dog, cat, left, right, anything where it's just two possible values. Now the Poisson distribution is a classical model for handling count data. And we'll use it a lot when I'm talking about rare events such as rare diseases. Well, that's all I've got for you. Take care and goodbye.